Ну, не так уж и долго. Базарили 20 минут. Ну, давайте, начинайте уже.
I want to incorporate this technology into my art and have the two mixed together.
We were making a lot of decisions where we thought things were going to be because we didn't have the compute power to support at the time what we wanted to do.
So at lunch one day, a Bell Labs executive asked, what would it take to ray trace this scene in real time? And I said, well, we need a 512 by 512 array of Cray supercomputers, each with a red, green, and blue light bulb on top, and we'll put it in the desert and fly over it at 10,000 feet and take pictures of it.
I recall it being sort of 10 or 12 months of hell getting these shots done, and it was because the render times were so horrendously long.
Fight one! Ready, go!
На 980-х можем воксели делать. А что-то после 980 ничего не показали больше. Типа 10 серии типа ничего нового не было по сравнению с 9, кроме тех процессов, похоже. Ну. Все то же самое, что и про Квадро будет рассказывать.
First of all, great job, guys. We're gonna kill it. Don't panic. Everything's gonna be fine. There is so much technology in this room right now. It's barely under control. Okay, so you guys are going to have a great show. Welcome to the launch of the GeForce
Ну-ка.
GTX
GeForce GTX все-таки.
1180.
1180. 1180. И он сейчас скажет хер вам.
I have never seen anything that leaked this much. The good news is you're going to be surprised. We didn't do it on purpose, but everything on the web, every spec is wrong. You're going to be surprised. It's going to be a great show. This is a historic moment. This is a historic moment for computer graphics. For as long as there has been computer graphics, it has been the dream of computer scientists to generate with computers photorealistic images. When you look at this, what we consider the holy grail of computer graphics, you see some effects that today are simply impossible to create. First of all, light is coming in from the window. It's bouncing all over this room. The vast majority of this room is being illuminated indirectly. Whenever light touches a material, strikes a material, that material is rendered and simulated physically. The material is metallic or dielectric, it's either smooth or rough. The roughness can come from microsurface structures that bounces light, absorbs light, diffuses light in a very different way. Maybe it's orientation dependent, maybe it's not. Some of it is glossy, some of it is matte, and as a result, this entire room looks alive. As light is bouncing around this entire room, it doesn't strike every surface the same way. Some of it is occluded from light. We call it ambient occlusion. You also see that there's a desk lamp, and it's shining through the glass, and because the glass has curvature and
Похоже, он
shape,
сейчас про
light
квадро
refracts around
RTX
it
будет
and
рассказывать.
accumulates in a way that we call caustics.
Вступление
A little
плохое.
bright reflection on the table is particularly attractive. The shadow of phasma coming from all different directions. It's called umbra and penumbra. Umbra is where the shadow is completely occluded, and penumbra is where it's partially occluded, and so you see the sense of soft shadows. She's reflected in the mirror, even the parts that you don't see. You know how mirrors work. You can see behind things. Oftentimes in video games we can't do that. The little bit of shadow behind that painting, ambient occlusion, or as light travels through those gummy bears, bounces around inside the gelatin, and then reflects and refracts it back out, called subsurface scattering. All of those little tiny effects are really, really hard to do. And the good news is, in 1979, a computer scientist named Turner
Странный
Whitted,
образ.
now
Еще
a
и теплая
researcher at
такая.
Nvidia, described an algorithm that was both powerful and elegant. He called it multi-bounce recursive ray tracing. By starting from your eye instead of from a light source where light is emitted, because the vast majority of the light doesn't reach your eyes, so there's no reason to trace them. He traced light backwards, inverse ray tracing. Through the eye, through the pixel, through every single pixel on the screen, the ray would seek out, would be sent forward, and if it were to strike a triangle, it would then send off a shadow ray to decide whether it's in shadow. That shadow ray would go towards the light sources. If there's something else in the way, if it strikes another triangle, it would determine that it was in shadow. And if it doesn't, then it would accumulate the color and the intensity of that light would then be used to shade that surface. If that beam of light, if that ray going through another pixel were to strike a reflective surface, it would generate shadow rays to see if it's in shadow, and it would also generate a reflected ray. a reflected ray, a reflection ray. That reflection ray would be basically the same incident angle relative to the normal of that surface where it struck. And then it would go off and decide whether it strikes another triangle, and if it were to strike another triangle, it would create shadow rays. It would determine whether that particular surface was in shadow or reflection rays and such. And if it was to hit into a surface that is translucent, then it would generate refraction rays based upon Snell's law. And that this algorithm, this basic algorithm, would recursively run. And eventually, he would generate this beautiful image. In 1979, he generated this image, and it took 1.5 hours on a $1 million VAX computer. Basically, he was generating 60 pixels per second. Instead of 60 frames per second, he was generating 60 pixels per second. And so the question then is, how long would it take for us from that time for us to be able to realize this incredibly beautiful picture that I just showed you a second ago? Well, if you look at our technology curve, has been nothing short of extraordinary. And ladies and gentlemen, you have so much to do with it. Because of the extraordinary demand of video games and the scale and the size and the vastness of this entire industry, it has propelled one of the most fast advancing technology in the history of computer science. If you look at this curve, Moore's law has been the foundational thought, the foundational idea of computer science for 35 years. And yet during this entire time, since our beginning, we have been moving at 10 times Moore's law. If you go back to when Moore's law was following historical levels of increasing performance 10 times every 5 years, 10 times every 5 years, or 100 times every 10 years, our GPU technology was advancing at 1,000 times every 10 years. 1,000 times every 10 years. And so the question is, and by the way, these are some of my favorite GPUs. Look at GeForce 256, the world's first GeForce. How many of you have GeForce 256? Incredible, thank you. Look how cute GeForce 256 is. At the time, so you know, at the time, it was the single largest chip ever built. It was bigger than a CPU. And people were shocked that we built something that big. And they were even more shocked that we could sell something that big. But anyways, GeForce 256. GeForce 3 was the world's first programmable shader. GeForce GTX 8800 was the first CUDA GPU. The most important GPU we had built up to that time. And then of course, the most powerful GPU in the world today, the GTX 1080. Well, if you were to plot out this trend and you were to think about how many rays it would take, you had billions of rays we have to send into that room, even though we're not simulating most of the rays, only the ones that are coming into our eyes. We're sending in billions of rays into that room. We've got diffuse rays that we have to do. We have reflection rays, refraction rays, and it's bouncing all over the world, all over the scene. And you have hundreds of polygons, hundreds of millions of polygons. The amount of computation necessary is easily in the several petaflops. Well, several petaflops, we're already at the teraflops today. So it would take approximately 10 more years, at our current rate of progress to go from teraflops to petaflops. Well, we didn't want to wait that long. We didn't want to wait that long. And as you know, architecture is the single greatest lever in computer graphics. It is the single greatest lever of GPUs. So what are the interesting new ideas we could create that allows us to achieve effectively 1,000 times more performance 10 years earlier? And so we invented the Nvidia RTX. The Nvidia RTX is a platform consisting of architecture and software and SDKs and libraries that allows us to combine different types of rendering technology into one unified and cohesive platform. Of course, it should always take advantage of rasterization. Rasterization is so incredibly powerful and so incredibly efficient, but we also need to include ray tracing. However, just ray tracing at brute force level simply won't get us there. It simply won't get us there. And in fact, I'll show you something later that's just really amazing. It simply won't get us there unless we use this technology we discovered about 6-7 years ago called deep learning or artificial intelligence. We can finally create images along with ray tracing that allows us to achieve the levels that we otherwise can't imagine. Now, we leverage two fundamental rendering technologies. You know very well rasterization, which is the way that we do things today. We start with the 3D world, and we take the 3D world information, the vertices, the triangles, and we project 3D world vertices into a 2D world pixel plane, into our screen space. That projection leaves the silhouette of a triangle, and we have to decide and test which one of the pixels are within that triangle. One of the most beautiful things about rasterization is that you could parallelize an enormous amount of calculation, and nothing is more beautiful than being able to do things in parallel. That's one of the reasons why the GPU is so incredibly powerful at parallel processing. It started with the idea of doing things in parallel. It also has the ability to do things incredibly high resolution, because high resolution is just more things in parallel. And so rasterization was incredibly powerful. One of its limitations, however, is that every single time you want to light the world, you have to project light from that light. And if you want 2 or 3 lights, that's fine. If you have an area light, that's effectively infinite number of lights. And if everything in the room were to reflect light, and everything in the room became a lighting surface, otherwise known as global illumination, in the world of global illumination, all of a sudden the number of lights that you would have to cast inside that scene is just insane, and therefore undoable. Well, this is where ray tracing is particularly effective, because ray tracing, using Turner-Whittett's approach, simply traces the number of pixels that comes into your eyes, the number of rays that ultimately reach your eyes. The vast majority of the rays inside this room, the vast majority of rays in the world simply never are reaching our eyes. And so we immediately reject them. We immediately don't have to do them. And we start from ray tracing our eyes. Ray tracing, whereas rasterization is taking 3D world data, projecting it in 2D, ray tracing is sending out a ray of light, intersecting the pixel at the screen space, and enters into the world looking for a triangle that it would intersect. The two basic approaches both has its strengths and weaknesses. In the case of ray tracing, in order to ray trace this entire room, the number of rays, the trillions of rays, the hundreds of millions of polygons, the amount of testing that you have to do just to figure out which ray intersected which polygon is just extraordinary. You simply can't do it. Well, we put this platform together, and we worked with Microsoft to create the DirectX ray tracing, otherwise known as DXR, the Microsoft DXR. And then we worked with Epic to integrate RTX, DXR, into the Unreal Engine, the UE4 engine. And we found somebody with extraordinary art assets, Industrial Light and Magic, and together we created the world's first real-time ray tracing demonstration. It had never been done before. And we announced it this year at GDC, and I think it's worthwhile to take a look at it, and I want to show you something special about it in just a second. Okay, so this is our demonstration.
Короче, вот этот новых они сделали на видеокарте полностью.
What's the story with all the elevators lately? I heard Kylo Ren destroyed the one over in D sector. If you ask me, who's ever in charge of this place should be transferred to Hoth. What? What? You think she heard us? I think she heard us. At least we blend in for once.
Incredible, right? Absolutely incredible. And so what you saw was physically based materials. It was sitting in an elevator shaft where there were area lights, and those area lights were moving as the elevator was moving. And therefore, as the area lights would illuminate the surfaces, and the shadows would be soft. The shadows would be soft. Using area lights is incredibly difficult to render shadows. And notice the inner reflection. There's reflection off of Phasma. There's inner reflection of Phasma on her gun. And there's reflection of her gun on her chest. And if you look at the stormtroopers, the illumination and reflections are all completely in real time. Doing this is simply impractical today. The way that you would do it, of course, is that you would fake a whole bunch of lights. That would slow down performance. It still won't look right, and all the shadows will look bandy. Second, you would create all kinds of what is called reflection probes made out of cube maps. But unfortunately, they're all moving. So every single scene, you're going to have to create a whole bunch more reflection probes, a whole bunch more cube maps, basically starting from the point that you would like to have to see reflection and rendering out from that point every single direction, turning into a cube reflection map. Those tricks simply are not practical with a scene of this level of fidelity. Well, it took 4 Tesla V100s, the same GPUs that are powering the world, 5 of the world's top 7 supercomputers today. It takes 4 of them in a $68,000 deep learning supercomputer that we make called the DGX. This is what researchers use to create their deep learning AI models. And so $68,000 to finally render running the RTX platform, real-time ray tracing at about 20 some odd frames per second. Well, when we announced it, people got so excited about it. They said, how do we buy that DGX? We could use it as a game console. And the requests just kept coming in. How do we turn DGX into a game console? The price point is slightly out of reach for most gamers. And so today, I would like to make my first announcement. Starting immediately, DGX.
$60,000.
$3,000 easy payments of $19.95. 3,000 easy payments. We'll throw in the first game for free. So call now. The telephone number is right below you. 1-889-789-2080. And good luck with that. It's beautiful, isn't it? That's just completely liquid cooled. It is silent, doesn't make a peep, and it does real-time ray tracing for the very first time for $68,000. Well, it turns out what you were looking at just now was not running on that. It was running on this little thing, this little bad guy. This is called Turing. We've been working on Turing now for almost 10 years. Trying, failing, all these different algorithms, trying, failing, and finally, Turing. The most advanced GPU we've ever done, 10 years in the making, the greatest leap since we created CUDA, and computer graphics will never be the same again. Inside Turing is 18.9 billion transistors. This GPU, this chip, is the second largest chip the world has ever made. The only other larger chip is called the V100, which powers supercomputers all over the world. It has 3 brand new processors. The SM is completely brand new, has the ability to do independent floating point and integer operations. And the reason for that is sometimes you're shading for color, sometimes you're using integer operations to calculate addresses so that you could run your shader program to do things like subsurface scattering. And as more and more special effects are to happen, the SM's address calculation part of the logic becomes much more complex. 14 teraflops and 14 integer operations per second. I like to shorten it just to 14 tips. So 14 teraflops and 14 tips. It also has the ability to do this thing I won't talk much about today, but we're going to write plenty about it, variable rate shading, so that we could do things like foveated rendering, focusing all of the horsepower to the GPU where your eyes are focused instead of wasting it evenly across the entire space. If you're moving, we might be able to adapt the place where we focus your shading horsepower. If the resolution or the content detail is different across the entire scene, as most scenes are, we could focus our horsepower where there's the greatest amount of fidelity. As a result, you're effectively getting a several X boost in your shading performance. The second is a processor we call the RT core. RT stands for Ray Tracing Core. It's 10 gigaраys per second. I love saying that, 10 gigaраys per second. A 1080 Ti, the fastest GPU in the world today, 1080 Ti does 1.21 you guys got, no? Nobody ever saw that show? 1.21 gigaраys per second, okay? And so we do 10 gigaраys per second, which is 10 times a 1080 Ti. It does I'll explain that in just a second, a BVH traversal, tree traversal, and it does ray triangle intersection testing. And then we have a new processor called Tensor Core, which runs AI processing like crazy. 110 floating point teraflops, or because it has multiple precisions, depending on the type of networks you're running, you might be able to use lower precision or mixed precision. As a result, 440 tops with 4-bit integer. All of this so that we could do hybrid rendering and run RTX. Well, so the question is, how does this all turn out? So if you look at the performance, it looks kind of like this. So Turing is built for RTX. And if we ran, the first thing I showed you was originally ran a GDC was DGX with 4 volts, 55 milliseconds, about 20 frames per second. And this is what Turing looks like. One Turing. So 4 volts in a DGX. This has never happened before. This has simply never happened before. Doing computer graphics, essentially a supercomputer replaced by one GPU within one generation. Of course, it took us 10 years working in parallel. If you were to look at Pascal, this is what Pascal looks like. The fastest GPU on the planet. The fastest GPU on the planet today. 1080 Ti, 308 milliseconds versus 45. Basically, about 8x. So the question is, what's happening under the hood? This is a new computing model, and so there's a new way to think about performance. It's a new computing model, so there needs to be new metrics. Back in the good old days, the vast majority of computation was done in shading. We're basically shading the color, or we're running a program in the shader, and basically we're shading. But in the future, we're going to be doing lighting, we're going to be doing all kinds of image processing, and so the pipeline is completely different. And if a pipeline is different, the platform software has got to be different, the architecture of the GPU has to be different, and you have to measure it differently. We have a new way of measuring, and let me talk to you about how we're going to do that. So if you look at this frame, this is abstracted, of course, but it's not too far off. Basically, within the frame that I was showing you earlier, we're doing ray tracing pretty much all the time. Okay, we're shooting rays all over the place. We're looking for intersections of triangles and figuring out which one of them has to generate shadow rays and which ones of them have to generate reflection rays and which one of them has to generate refraction rays. And for the reflected rays, it's got to figure out how many more shadow rays it's got to generate. And so all those rays are being bouncing all over the place. And eventually, we accumulate the color, the intensity, whether it's directly or from something nearby, and we shade that surface. And so we're ray tracing all the time. And that's with our RT core. That's the amount of time, the fraction of time within 22 milliseconds that an RT core is doing it. Imagine if we didn't have the RT core, multiply that by 10. If we didn't have an RT core, that green bar, just simply in terms of time, is just 10 times larger. So basically, all the way down the street. Shading is shading. We're doing shading incredibly well. One of the things that's really great about Turing shader is that we can now overlap or run independently floating point integer, and as a result, it's, call it 1.5 times more performant than it used to be. And then that's the integer shading there. And then for DNN processing, when everything is done, we could use it to generate pixels that we haven't finished, to generate using artificial intelligence the pixel that we haven't finished, or use artificial intelligence to generate resolution that we otherwise couldn't have. Okay? It is possible to filter information, but it's very, very difficult to generate new information that looks right. And so with artificial intelligence, we can now, for the very first time, generate missing pixels that are actually right. And we could do it in real time because we have the tensor core. And so if this is what's going on in the frame, then what's happening inside our chip? So the first part of that processing, the shader and the RT core, the Turing SM and the RT core are both concurrently running. Later on, we're shading and running other parts of the program, the shader program. And so those two parts are running, the FP and the integer. And then finally, when everything is done, we're going to use artificial intelligence. All of our 110 teraflops. 110 teraflops, think of that, is basically 10 1080 Ti's. It's basically 10 1080 Ti's dedicated to doing one thing, which is artificial intelligence. And so if you just simply do the math, you have about 14 teraflops of shader math. You have 110 teraflops effectively of ray tracing. 14 plus 14 independent teraflops and TIPS. And then lastly, 110 FP16 tensor core processing floating point operations per second. When you take that and do the weighted average on it, it's basically 78 tera RTX ops per second. And so the way to think about performance in the future is to figure out a way to weight all of these different types of processors. And so the way we think about Turing is 78 tera RTX ops. Okay? Compare that to a Titan X, our highest end of approximately 12. 78 versus 12. When you're running ray tracing, that's what it's going to look like, 78 versus 12. Well, one of the most important miracles, you're going to see a lot of writing about this in the future, is simply the testing. The concept is simple. You're sending an array into the scene, and you're trying to figure out which one of those triangles out of 100 million that intersects. Well, you could simply just walk across the screen and see which one you eventually touch. Well, you got to go 100 million times. Or what you could do is you create a data structure, an acceleration data structure, called a bounding volume hierarchy. Basically, it's like binning. Suppose I had 10 things I got to figure out which one is the one I want. I was asked to go pick something out. I had to go pick one of 1,000. I'm going to put 10 bins or 10 boxes, and within each one of them, I'll have 100 things. Within each box, I'll have 10 boxes with 10 things each. If I knew that, as I started looking for that thing out of those boxes, and I discovered that it is in one of those larger boxes, then I can ignore every other box. And then once I find it within the larger boxes, if I find it within one of the 10 smaller boxes, I can ignore all of the other boxes. And then if I can find it within that box, I know it's one of the 10. It's the same idea here. We're sending this triangle, we're sending out this ray, we're trying to figure out which one of the triangles it intersects with. And once it intersects with a bounding box, which is a large structure, which has a whole bunch of other bounding boxes within it, which other boxes within it, and within that, there's a whole bunch of triangles. Once we intersect one of the bounding boxes, we know all the other bounding boxes are ignored. And then we figure out which one of the bounding boxes within, and then once we figure out which one of the bounding boxes within, we have to figure out which one of the triangles it happens to be. Well, the amount of mathematics necessary to do this is just shocking. And to do it precisely so that the image quality is perfect is really, really hard. And it took us 10 years to do this. To create the architecture and the algorithm for doing this, design it in a way that actually speeds up, which is very, very hard to do because these beams, all these rays are incoherent, which is the enemy of parallelism. Somehow, we figured out a way to make all these incoherent things largely parallel, and then to create an acceleration structure, an accelerator that allows us to do this at the speed of light. And so, the RT core was invented. Well, the RT core invention had to go along with all the software layer on top of it and what we call eventually the RTX platform. At SIGGRAPH, we were really pleased to see research being done in this area. Our researchers and the researchers at the Search for Extraordinary Experience, I love that, SEED, Electronic Arts' research team. Nvidia Research is called Nvidia Research. EA Research is called SEED. I love that. The Search for Extraordinary Experience Division. And so they worked on RTX with our researchers to figure out how it could accelerate, how it could create new computer graphics. And everything from deferred shading and direct shadows and lighting and reflections and global illumination and ambient occlusion, transparency and translucency. Translucency and transparency are just incredibly hard to do with rasterization because the concept of depth is very difficult to discern. And post-processing, as you could see, for each one of these operations, we're using different parts of the chip, exactly as I described earlier. The effective ops, the effective computational capability, 6 times Volta. 6 times Volta, 6 times NVIDIA V100. And so that kind of puts it in perspective. This new Turing processor, this new Turing GPU is just a monster. It's incredible. Let's take a look at some of this stuff. And so this is what it looks like. This is computer graphics today. Physically based material, direct lighting. You could see the shadows. They're hard shadows. We could try to trick it by blurring it a little bit, but it's still going to be basically that. And this is what RTX looks like. Okay, so hey, you got to clap at the old stuff too because, you know, it resembles us. So, here we go. I'll give you a chance. Guys. This is where we came from. You got to be proud of it. You got to own it. It's ugly, but you got to own it. Before, after. Before RTX, after RTX. Oh no, this is just the beginning. I'm just warming you guys up. I just gave you an olive for the appetizer. Okay, can we show them some stuff? Nacho,
Hi.
Is it you and me?
Yes.
Okay, so this is Nacho. He's one of our dev techs, incredible computer scientist, amazing computer graphics engineer. This is what he was able to do with RTX off. RTX off. Now, of course, this scene is incredibly hard, and the reason for that is because you can't use tricks like screen space reflection here. You could put some reflection probes, but it's just incredibly hard here because things are being reflected all over the place. There's refraction. You see that graphics card back there? That's a beautiful graphics card. I announced it a week ago. That's called the Quadro RTX. And you got this crystal ball here where it should reflect and refract. There's a little green ball on the ground there, and then there's that chrome ball in the back, and this empty, I don't know why, but empty glass box. And it's got area light coming in, which is really hard to do. Okay? And so in this particular case, Ignacio is doing his best to emulate the area lights, but the shadows are ugly. This is the limits of today's computer graphics. Now, we could fake a lot of stuff. We could fake a lot of stuff by arting it up and cause you to not look at it. But in the final analysis, this is what the limits of today's computer graphics is. Now, Ignacio, let's turn RTX on. So let's take a look at RTX on. Look what happens. The refraction of the glass globe there is just incredible. And look at this, the little caustics on the ground. The area lights cast a soft shadow. The umbra and the penumbra, notice of the graphics card. The shadow of the chrome ball looks right. Now there's reflection of the glass box in the RTX, Quadro RTX. You see Quadro RTX from that sphere, and you see the reflection of the chrome ball with a little bit of rough surface to give you a sense of material. Everything just kind of looks right. Even the glass is casting a shadow. Even the glass is casting a shadow. Hey, let's go back to the last one again. Yeah, I know. Now, of course, we got to add a whole bunch of paint and a whole bunch of stuff to make it look right, or we could do it this way. RTX on.
Время рендера бы еще поставил.
And there was a gasp in the audience. But this could possibly be a photograph, right? Nacho, show me what you got. Oh, come on. Okay. Pretty incredible. You had to turn on a spotlight on top of that. Everything just works. Everything just works. Look, glass reflects and refracts and magnifies just like it's supposed to. And you just have to turn it on. And so the benefit of RTX is just turn it on. Thank you. Good job. And so now I'm going to show you something. We're going to turn it on together. We're going to put it all in. We're going to put it all together. And it's going to be a demonstration that we created recently. To highlight the power of Nvidia RTX, this mixed mode rendering, unifying rasterization, ray tracing, compute, and artificial intelligence. And what you're about to see is completely in real time. Everything you're about to see is completely in real time. It's kind of hard to grok because it's going to be so beautiful, but it's completely in real time. You're going to see beautiful reflections. You're going to see inter-reflections, reflections of reflections, and it's all going to be dynamic. You're going to see beautiful lighting. You're going to see area lights. You're going to see beautiful ambient occlusion. You're going to see beautiful physically modeled materials. So things that look like metal looks like metal. Things that look like things look like things. That's very technical. And that's how I talk to the engineers. Guys, we got to make things that are things look like things. And they go, I know what you want, boss. And so what's in here is just really a miracle. And it's running on one Turing GPU. It's running on one Turing GPU. Ladies and gentlemen, the name of our demo is called Sol, S-O-L. What do you guys think? The Nvidia RTX. Nvidia RTX running on top of a Turing GPU. Hybrid rendering, real-time ray tracing for the very first time. That's the first part. Deep learning is the single most powerful computer technology that has come onto the scene in the last 30 years. Deep learning is a field of machine learning where using a large amount of data, you could train a supremely large neural network how to do things. You train these neural networks with all of this massive amounts of data, which is otherwise examples, on supercomputers. And this is the reason why voice recognition, natural language understanding, photo tagging, image recognition, all of these amazing feats of software are now finally possible. It is the reason why self-driving cars is even within reason to fathom. Deep learning is changing one industry after another. And people consider this the fourth industrial revolution. It is going to enable AI and computers to write software by itself, to basically run on a supercomputer, to write software by itself. At NVIDIA, we're doing all kinds of research around deep learning. We have a gigantic supercomputer that all of our researchers use to develop software. Now, some of the things that are, I'm showing you some examples here. These are some of my favorites, but there's so many. For example, you could teach a neural network how to colorize by just showing this neural network examples of, this is a black and white, this is how you colorize it, this is black and white, this is how you colorize it. It eventually learns what the pattern is, and you can give it a black and white image, and it colorizes it. You could teach a network how to take a low-resolution image and make it higher resolution. Because you and I could look at this image and say to ourselves, you know what? I bet I know what pixel each one of those pixels are. And so you could use a low-resolution image input and eventually get an output of a high-resolution image by going the other way, which is starting with a high-resolution image and give this neural network the opportunity to generate that, and whenever it's wrong, you correct it using this thing called stochastic gradient descent and backpropagation. And so you literally correct it, and it tries to guess and guess and guess, and it corrects itself until one day it's able to figure out what pixels to generate. You could teach it how to take a cartoon and turn it into live video. This is a piece of work that we did in NVIDIA research. Okay, we simply taught it how to do that. Pretty amazing, right? We could teach it to take a low-resolution CT scan and not only increase the resolution of it, but also segment it, figure out what organ is what from that blurry blue image. Okay, you watch this? We taught it how to segment, how to identify which organ is what, and put a different color around it. Pretty amazing. This is going to revolutionize medical imaging. We have a platform called Clara. It has the ability, you could teach it how to go find identical twins. Come on, you guys, that was funny. This is what we taught it to do. Change the color of the hair. All in real time. Previously, you would have to find identical twins to do that. Much harder. Now you could do it with an artificial intelligence network. You could take a sketch and turn it into 3D. So you take this neural network, you give it a whole bunch of examples, you tell it what is the input and what is the exact expected output, and we give it a chance to try again, trillions and trillions of times on a supercomputer. Eventually, it trains and does this amazing thing. And then it creates this neural network model with hundreds of millions of parameters or hundreds of gigaflops of operation necessary to perform its task, to either classify, to predict, to draw, to generate, to imagine what color looks like. We could teach it to do these amazing things. However, there are so many architectures, and it takes so much processing to do it in real time. And so we created this thing called a tensor core. There are a whole bunch of them in our chip. And imagine this, okay? Imagine that a 1080 Ti is 1080 Ti is what, 11 teraflops. A full 1080 Ti, a full 1080 Ti at $699 is 11 teraflops. This is 110 teraflops. Basically, it would take 10 full 1080 Ti's to keep up with the tensor core processor that's all over the Turing GPU. Now, one of the things that we taught it to do is something really incredible. And so we taught the neural network this thing, and we're calling it the Nvidia DLSS, Deep Learning Super Sample. Basically works like this. We create a whole bunch of super, super high resolution images with lots and lots of samples. So we jitter it and we create basically 64 amazing images, and we create hundreds of thousands of those. And then we give our network, we put an image in here, and we say, using this, it's called an autoencoder, convolutional autoencoder. It has to be temporally stable because we want to do this for live action. And so the network has to remember part of the past. And we're going to give it an image, and we're saying, go generate this amazing image on the output. Okay? So pretty soon we'll be able to give it a new image it's never seen. We train it, and every time we train it, if it guesses wrong, we tell it what's the right answer, we propagate it back. It takes another image, it guesses it again, and if it turns out to be wrong, we propagate it back. And we sit there and we just simply loop on it on a supercomputer. We run it trillions of times. And then eventually you put in an image and it creates this beautiful image out. You create you take an image of lower resolution, say 1440p, and it creates this beautiful, beautiful image that's 4K. Now, of course, the question is, where did the images come from? Where did that come from? Where did that magic come from? It came from partly a supercomputer. Essentially, what deep learning is doing is codifying the memories of a supercomputer, and it puts it into this neural network, basically an image generation brain. And you put this image generation brain, this neural brain, into the mathematics of our GPU. All of a sudden, it knows when it sees this image, a better version of it is that. And it sees a new image, a better version of it is that. That mathematics came about, the weights of those neurons came about because of a supercomputer. And so in the future, every game would have had the benefit of supercomputer pre-processing before you play it. And we call that platform the Nvidia NGX. In the future, computer graphics will merge with neural net processing. We call it neural graphics acceleration, NGX. It's a framework for doing all kinds of amazing image processing. You saw earlier super resolution. We've invented super slow-mo. We're going to do all kinds of amazing things that makes video games and the images that come out of these computer graphics, CGI, look even more amazing. Basically, it works like this. We have a supercomputing infrastructure. There's a whole bunch of software that runs on it. The first thing you do is you generate ground truth. What is the perfect image? What is the perfect image? And then we have to train this model. It's a multi-dimensional manifold, and we're basically randomly walking around this manifold looking for the least error, looking for the time when you send in an image, the output is closest, your predicted output is closest to what ground truth is. Okay? That your prediction is the closest to ground truth. And you're sitting here wandering around this gigantic universe, and it's incredibly, incredibly large. And so the computation time is very, very long. And that's why we build these supercomputers we call DGX. I showed you earlier version, the desk side version with 4 GPUs. These ones have 8. And then we test and optimize it. Then you put in a low resolution image or lower quality image, or the image is in fact not even complete with ray tracing, and somehow we complete it. Somehow we make it more beautiful. The Nvidia NGX. And then we have this AI model that we then OTA to you. You download it into your driver, into this plug-in interface called NGX, and the neural networks are changing all the time. They're getting better and better, and we put it up in the cloud, and you can decide whether you want to enhance your images or not. Then you run that on Turing. NGX driver. This is all part of the RTX platform, and you run it on the chip. Well, the supercomputer looks like this. This is the machine that is generating all of those networks. And basically, before you even run it on Turing, before you even run your game on Turing, there are a bunch of supercomputers here's one. There's a bunch of supercomputers that's training these models. And the graphics card, here's one. The graphics card, you guys know what a graphics card looks like, right? Here's one, available retail, $68,000. Okay. Got to keep your abs tight while you're doing this. A whole bunch of interconnects, SerDes interconnects called NVLink, connects all of these GPUs together into one virtual GPU. Every single GPU can see each other's GPU memory. All together, this board, that system has 2 of these inside. 2 of them. This is 1 petaflops. That's another petaflop, not motherboard, but mother of, God, it's heavy. GPU, 2 graphics cards. Makes 2 petaflops. 2 petaflops, you want to put 2 petaflops is basically a supercomputer with servers from that side to that side. 400 servers, $2 million without anything else of servers this replaces. And so we use this to train the neural network model. Here we go. Here. You could do it. Thanks, Paul. You use that, and you train this network called the Nvidia DLSS. Okay? And then it comes up with a model like this, and this is 4K TAA. You guys know the Unreal Engine Epic's demo called Infiltrator. It's just beautiful. Incredibly taxing on systems. And 4K TAA up there. TAA is the anti-aliasing technology we invented, which is temporal. And so temporal, it takes last frame, the motion vectors, and it tries to figure out what's the best combination to create beautiful edges. Look at that, because it's temporal and the motion vectors, so many things are moving. You see a disjointed hinge over here. And this is 4K DLSS. Look at this. That's just perfect. Okay? Well, for the very first time, because of this, because we could take a lower resolution image, and because we could train a neural network with all kinds of super high resolution and super high quality images, this neural network, it runs on a bat out of hell processor called a tensor core, could then in real time enhance images. In real time, generate pixels it had never seen before. Generate pixels that make sense to go there. Because if you and I were to look at it, we would know what makes sense to go there. And therefore, it makes sense that we could teach a neural network how to make sense of what pixels to put there. So I'm going to show you something. This is Infiltrator running on 1 GPU at 78 frames per second in 4K at a quality that has never been seen before. A 1080 Ti, the fastest GPU in the world, can currently do about 30-something. Okay? From 30-something, what you're about to see is 4K. Now, I'm going to lock it to 60 hertz because this display happens to be V-synced. And so you're going to see the frame rate on top, and ideally, it's pretty high. Very first time to see Infiltrator running at 60 hertz in 4K.
Презентация игры, я так понимаю. 60 FPS.
Is that amazing? It's just silky smooth. Silky smooth. One Turing GPU, twice the performance of the highest end GPU in the world today, 1080 Ti, running at 4K with beautiful image quality. Well, you know, we should probably at this point take a look at what Turing does and RTX does for games. You guys want to see some games? Kata, what do you have for us?
Thanks, Jensen. Yeah. So,
You need your mic on, sir.
oh, testing 1, 2.
Yeah.
So,
Ladies and gentlemen, Kata,
all right. So first up, we have
head of our developer relations. We work so closely with developers all around the world. We work with them to improve new technology, create new technology, and optimize their games for our platforms and push the limits of what's possible in real-time computer graphics. And the work that we all do together it just brings me so much joy. And we got this amazing developer relations teams that works with them and dev tech team and all these computer scientists that work with them. And man, it's just so great. I love you guys.
in my 17 years here, Jensen, our entire team has never been more excited over a new technology, a new product than with Turing, and also with the developer reception has been phenomenal, and we're just so pumped. It's really an honor to be here to deliver.
Kata, you know what?
Games.
I'm going to give every DevRel and every dev tech in our company a new Turing.
Oh my God. Oh. Thank you. Wow.
The number of people in that group, I'm sure, has increased by a factor of 10 since I said that. Okay, what's the first game we're going to talk about?
So Shadow of the Tomb Raider is the first up. It's the latest and the really, obviously, not much needs to be said. It's a super successful franchise. Just data-wise, it sold 65 million units, and it's going to ship the Shadow of the Tomb Raider on September 14th. This time, the game has Lara Croft going on an epic adventure in Mesoamerica and South America. Just one thing to note, a parallel, Lara has a long and illustrious history, and actually, in many ways, Lara and Nvidia has grown up together because we both
Never thought of it that way.
Yeah, in the mid-'90s.
Yeah.
And in fact, Jensen, it happens to be the first game I played when I bought my first Riva 128 in 19.
I was 30 when she was 25. Grew up together.
So yeah, so we work for Crystal Dynamics, Nixies, and IDOS Montreal, and we're excited to be able to show it.
And now what we're going to feature, we're going to show just a little part of it. Then later, there's an after show, and the developers are going to talk to you about all this. You're going to be able to see all this stuff. But we're going to show you just a few things about it. So one of the things, of course, Lara Croft, you're in shadow all the time. It's all about shadows. And one of the challenges with shadows, as you know, they're just, using traditional shadows, they're too crisp. And so they have these hard shadows. And if we use contact hardening, and we use percentage closeness shadows, they're kind of blurry and fuzzy and noisy, and when you put a whole bunch of them together, it just becomes a big mess. And so what you're looking at is ray trace shadows. And you're going to see a lot of ray trace shadow stuff, and that's the first demo we're going to show you. We're going to feature ray trace shadows. Go, take it away, guys.
Hey. My name's
Chad.
Hey, I'm over here. And apparently I work in the DevRel team with Kata, and apparently I just got a new Turing, so I'm really excited.
Bingo.
So what we did is we worked with Nixie's and IDOS Montreal to bring real-time ray-traced shadows to shadow the Tomb Raider. It's perfect.
And so the thing to look at right now with RTX off, you saw the crisp shadows up there, and you saw right here. This is really hard to do, and that's why they don't do it at all, which is dynamic lights and shadows.
These are dynamic point lights. They're really expensive to do in current rendering techniques because basically you have to cast shadows in every direction from the light. And this goes back to what you were saying earlier about having to put a cube map here and a cube map here, and every time you move, you have to redo all that rendering. So let's put RTX to the test and have it just do it for us.
Aww. The beautiful thing about ray tracing is you turn it on. You know, when you turn on the light, it just does the right thing physically. And because we're tracing these rays physically, it should perform according to what we expect.
Yeah,
and so the umbras, where right behind, where it's nice and dark, it's correct. And where penumbra, where you have the softness of the shadow, because not all of the shadow is occluded, part of it is lit, you get some softness.
Yeah. Off and on.
Wow.
Now let's take you were talking about some of those area lights earlier. You want to look at some examples of those?
Yeah.
Well, here's a big example. This is an incredibly lit scene. This whole scene is amazing. It's beautiful. And so what we have here is we have 2 cone lights and 2 area lights. Those area lights are basically rectangular shapes, the neon lights above the stage. And what you notice is the shadows below are hard, like you keep talking. And this is state-of-the-art for real-time graphics right now. And I got to say that because the guys are sitting right next to me who made those shadows. And they are, Brett. This is the best we have right now.
And they look beautiful.
Yeah, they look great.
Until now. And the way that's simulated, those area lights are simulated essentially as a couple of point lights. And that's why you see such hard shadows.
Exactly.
But if you simulate the area lights like area lights, because we ray traced it, and independent of where the rays bounced around, eventually, if it were to hit some part of that area light, it gets lit. And so ray tracing is a much more cost-effective, in fact, however, very difficult to do, way of doing area lights.
And let's turn this on and take a look. So you get the nice blend of the color and the light.
Isn't that beautiful, guys?
It's rather.
And we can do whatever we like. We could add more area lights. We could add more spotlights. You can mix it all together without trying to fidget with it, without trying to figure out what is the definition of right. Right just looks right. That's another wisdom. Right looks right.
And talking to the artists that do this, they tell me all great things about shadows. They're telling me shadow is another color to them. They love shadow. And they also told me that shadow and light is what they use to set the mood and tone of their environments. And so that's how important shadows are. And it feels like we just gave them a lot more depth for it. Some more on, more off.
Okay. What you got?
Well, we want to take a look at some more area lights that are very interesting.
Let's take a look at one more shadow.
All right. One more shadow.
Edge. Może.
works, the Umbra works, the Penumbra works. Everything just works. Okay, all right, man. Good job, Chad.
Thanks.
Guys, let's take a look at an exclusive trailer of the Shadow of the Tomb Raider.
What is that?
That's awesome. I can't wait. That's going to be a wonderful game. All right, what's up next?
Well, another blockbuster, and this time we have Metro Exodus by 4A Games.
Oh, man.
Yeah. So for those of you who don't know, it's the third in the Metro series. This is set to take place in 2036 in the post-apocalyptic wasteland of the former Russian Federation. You guys know this. It's been super successful. In just 2 versions of the game, they've sold 7 million units. And this one, Metro Exodus, is due out February 22nd of next year. It's going to be well worth the wait. It's developed by 4A Games, who, since for the first time we met with them, Jensen, back in 2009, they're super enthusiastic and very forward-thinking, so we're not surprised that we have them here today to show something awesome.
Yeah, that's really cool. Now, the thing that we're going to showcase with this demo here is something that is just really, really hard. Basically, the way light works is, can you guys see this? My light is really bright, but basically, light is coming in from the outside through those windows. And of course, this part is lit directly. And the challenge here is that's an area light, and so we have to make sure that the shadows look right. However, that light doesn't stop there. That light bounces around this room, and it illuminates different parts of the scene, depending on how close they are to that particular light. And maybe in the creases and the corners, it's really super dark, but in other places, it's more light, and direct light, it's completely bright. And so lighting this room using traditional computer graphics lighting is just incredibly hard. And this is the perfect showcase for global illumination. Now they want to use light, of course, to create these incredible moods. And so you feel, a little scared when you walk into a room, instead of being completely black, which is not right, or completely lit, which is not right either. And so global illumination has the ability to create an aura, a feeling, a sensation that is really photoreal. And so this has been something that we've been pursuing literally for a long time. This is a 10-year pursuit that we have finally been able to do, global illumination. Let's take it away. So Matt, this is GI on. And so just as I was describing earlier, the light is coming in through the window. It's bouncing around inside, and as a result, we're lighting. Look at that. That corner is darker. That corner over there is completely dark. And that light right above the windshield is nicely lit. It does exactly what you expect it to do. And it does it all by itself. Just put sunlight outside. Super high intensity ambient light. Put it outside and everything just works. Everything just works. Now you could do it the other way. No, go to direct light. You see this? This is the way computer graphics basically works. Now, of course, we could create a whole bunch more fake lights. We can create a whole bunch more fake lights. But in this room, if you created more fake lights using spotlights, you'll get all these different areas that are lit too intensely and others that are not. And it looks like you basically turned on a whole bunch of lights. Now, what you could do, and what Matt did earlier, is turn on basically an artificial global illumination light, which is basically a fake ambient light. It's like somebody comes in here, and instead of allowing us to light this room with global illumination, which is happening right now from these monitors, like for example, I'm being lit by the monitor, and you guys are all being lit by this screen, this 4K gigantic, beautiful screen. And so the entire room is being lit with indirect lighting. But here, because we can't do indirect lighting back in the past, as in yesterday, we had to put a fake light in here. It's like somebody comes in here and put a fake light and constant intensity, constant color throughout this entire room. As a result, the places that should be dark, like back there, isn't dark. The places that should be more bright is the same intensity. Okay, which is what you're looking at now. So this is wrong, and let's look at right. Look at that. Delightful. So Matt, our friends are now able to have like creepy monsters literally squatting in the corner.
Yeah. Take a look in the rafters in the ceiling. When RTX is on, they're black. I could hide anything in there. But if I'm lighting it ambiently, you can see everything up there. When we have RTX on, it's correct. There's no light up there, so we can actually hide things in. We can make the mood and the environment perfect by just letting the normal light in the room.
Games will never be the same.
No, sir.
So scary. All right, good job. Thank you. Let's take a look at another exclusive trailer, shall we? Metro.
Поэтому трейлер на метро выглядел так реалистичная презентация.
Wow. That is incredibly scary. I don't think we have enough arrows. Okay, I want to flash through a couple of them, and then in the after show, we're going to show it to you. I want to save time for a whole bunch more stuff. Okay, let me show you. Assetto Corsa Competiziano. That's Italian. I spoke 2 languages today already. Okay, when you guys see it later, I want you guys to look at some stuff. Okay, first of all, the reflection on the windshield. You guys know how screen space reflection works. If it's not on the screen, there's no way to take that image and reflect it onto the surface. And as a result, look at the glass on top. You see that car, you see the Ferrari up there? It's reflected on top. All of the rails all the way down are reflected. No errors, no weird banding, no weird distortions. You see the sky reflected from the other side. So when you go see it, He'll be moving, and everything will be dynamic. When the cars come through, you'll see all the reflections up and down this aisle of the cars with other cars, the cars over the window. Everything is going to be completely dynamic, and nothing had to be tweaked. Ray traced reflections and ray traced inter-reflections. Cars are going to reflect each other. If you look at the railing, the shadows are just rendered beautifully, the soft shadows, because the world is one big area light. And shadow map precisions are just not good enough to go all the way down there. And yet, for ray tracing, it just works. In fact, if you see the final game the other way, the shadows of the last buildings are completely gone. You're going to see reflections of the toolbox of the garage and the car in the garage. Everything just works. Global illumination just works. Ambient occlusion just works. All of the soft shadows underneath the cars just work. And you can look through the window, and depending on the angle of your view, you'll see Fresnel reflection. So sometimes you see perfect reflection. Sometimes you'll see through the car. Everything just works because ray tracing just works. You're going to see another game called Atomic Heart. And this game is just really interesting. And it's got wonderful reflections and refractions. And mirrors are curved. Curved mirrors. Nobody does that. It's impossible. Not for ray tracing. It just works. You get this area light underneath, casting that soft shadow for the robot behind it. Everything is physically based. All the materials are rendered beautifully. And so area lights, reflections of the scene that you can't see in the scene. So screen space just doesn't work. And yet everything just works here. Well, guys, I want to show you something that's really cool. You guys want to see an amazing game? I can't wait for this. This is probably one of my family's favorite games. And this is wow. Guys, I can't wait. I think we have with us Jonas and Christian from DICE. Guys.
Hello, Jensen. Hello.
Some of the brightest and the most amazing computer graphics engineers in the world. We've been working together on implementing RTX into Battlefield 5. Now, you guys, the anticipation of Battlefield 5 is so great, I don't think I need to introduce what is the concept of Battlefield 5. It is a World War II FPS. It is part history, part travel, part time travel, part running for your life, part destruction, real-time destruction. You've never seen destruction like there is destruction. Isn't that right, guys?
Correct.
You guys know destruction.
We do.
You guys know how to blow it up. Okay? There's mayhem, there's chaos. You work as a team, you can battle by yourself. I want to go learn all kinds of stuff about World War II by going through your game. I just want to be a tourist. Turn on God mode and go through as a tourist. So we're going to show you some pretty amazing stuff. Isn't that right, guys?
That's
all
right.
Okay, Jonas, let's go. Take it away.
Yep, Christian.
All right. Thank you, Jensen. Thank you, Nvidia, for hosting such a great show. This is really cool. I'm Christian. I'm a tech director for Engine Group at DICE, and next to me we have Jonas, media and video editor. We're here to show you our implementation, our vision, our take on what RTX can be, and we want to show that in our brand new Battlefield 5. And in the setting, we'll take a look at our brand new multiplayer map, Rotterdam. And it's a really dense and cool city map. We'll start here in a very zoomed-in view of the soldier's eye. And we're going to observe something that we've never really been able to do before. So we at DICE have worked closely with Nvidia engineers over the past year to get to the point where we are now. And we're so proud and thrilled to be here and show it off to all of you. So, Jonas, I'll leave it to you. Take it away.
Yeah. So, what you're seeing there is a tank firing off screen, being reflected in the character's eye.
Now, you guys know this is not possible
Now-
with screen space reflection, right, Jonas?
Exactly. This is
Because the fire is not on the screen.
So now if we turn around and we then see the environment, we can see that the tank muzzle flash not only reflects in the eye, it reflects in the entire environment in the tram windows there and within the tank itself, moving here. So now if we keep moving forward, yeah. That's great. So of course, one of the big challenges of SSR is also complex surfaces like this. So now with RTX on, if we set off an explosion behind the tank here, but next to the car,
Oh,
see
come
it
on.
reflecting accurately within the car.
That's impossible.
Of course.
How would you do that with RTX off?
Yeah, how does that look? Like this here. So let's, yeah.
Wow, that
back
looks
on.
incredible.
And it's, of course, it's updating dynamically, everything.
Reflections will never be the same again.
Completely
Look at the
fine.
reflections off the ground, guys. It just,
Yeah, so you can see.
wow, it just happens.
With SSR, if it's in the screen space, you still get some of the reflections upon the car, but due to the nature of SSR, it disappears as it goes away. But because ray tracing just works, you just get the expected result, how you'd think you would see it. So the next thing we have to show you is the big, scary crocodile tank, the Churchill. And if we make that one shoot, it's flamethrower across the scene here. Then we will again see that reflecting upon the surface and on the soldiers battling it out here in Rotterdam. So now if we look down in the ground with RTX on, we'll see the flame, we'll see the soldiers moving, we'll see everything. And now if I turn RTX off, we lose everything. We lose all the detail, all the context of what's happening in the scene. But with RTX on, you just get a much more cohesive image and a better understanding of what's happening around you. So one thing we also pay particularly much attention to in battlefields is just the weapons, accuracy, making sure the smallest detail is correct. And you can see even there, the flames are reflecting properly in the wood of this gun here and in the windows in the back. Now, if I turn RTX off again, you lose all this detail. So, yeah.
Wow.
Really cool.
Now,
tech.
Jonas, what you guys have done is all of your guns, all of the objects are modeled physically.
Exactly.
It's physically based. And so the gun has wood, which is diffused, is a dielectric material. You have metal, which is reflective, and the metal has substructure in it, microstructure in it, so there's some roughness in it. And so without doing anything at all, because it's physically based, we shoot a ray into that scene. It intersects with a triangle on that piece of metal on the site, and it figures out, I need to boink, generate another reflection ray, and it traces its way to the flame, which is coming by, and when it comes by, it accumulates on the surface, it shades it perfectly all by itself. Ladies and gentlemen, the magic of ray tracing.
Exactly. And there's more. So what you see now are objects that are really close by, but ray tracing works for more yet. So up here we've got two C-47 airplanes. They've been shot down, they're crashing with their engines on fire. So now if we go over to the car here, and you can also see the flame reflecting in the car nicely over there. So if we keep moving forward and then look down on this reflective car right here, we will still be able to see the plane. If we move back here, we can see the plane reflecting in the car. If I move this lens flare.
Wow, your lens flare works
right
good.
there, yeah. And then with RTX off,
I love
lose
it.
everything of it.
Yeah, look at that.
We can keep moving forward.
Wow. And Jonas, you guys did a great job with Fresnel reflection. Look when the angle is just right, it's just a perfect mirror. It looks beautiful.
Exactly. So here it's a good example on transparent surfaces with Fresnel and PBR rendering. The more of an angle you're at, the stronger the reflection gets. And now with what we had before, on these ones were just cube maps, which they're also static, but with ray trace you get a lot more detail. You see the entire environment. And of course, as I said, the old school cube maps, they are also static. So say that we were to destroy this building here, make a tank shoot it, with ray tracing on, you'll be able to see Frostbite's and Battlefield's destruction system within the window, moving dynamically. And now, to end it all off, RTX, I mean, it works on the entire scene. So what if we were to shoot off a V1 rocket here and zoom out, get a good view of the entire street of Rotterdam, and then take a look at the windows, all the places that you would expect to reflect. For now, turn up the time again, and we just wait patiently for the V1 to hit the ground. And there.
That's awesome. That's great. Good job, you guys. Good job. That's really great. And it's amazing what you guys did so fast. I know you guys worked super hard, but it's amazing how you guys implemented this stuff so fast. I mean, that's one of the benefits of ray tracing. You know, the benefits of ray tracing is because things are going to behave physically. You should be able to turn things on. If the rest of your system and your models are done properly, you could turn these effects on relatively easily. I mean, it still takes a great deal of great engineering, but comparing to doing it the traditional way of arting everything into existence, the amount of engineering that has to be done is just significantly lower going forward. You know, hopefully, using the laws of physics, when you guys create a scene, things would just look right and behave accordingly. And so this is really just such a great achievement. Wow, things are still falling apart.
Yeah.
I've never given a talk in total destruction before. You guys do destruction great. You're great at destruction. That's a lot of pent-up anger there, sir. Lots of great destruction. Okay, you guys made an amazing trailer. Let's take a look at it. Wow, you guys killed it. You guys killed it. Real-time ray tracing, Battlefield 5. And we have a great surprise for you today. Battlefield 5, open beta, September 6th. Guys, congratulations on a great achievement. Yeah, this is really a wonderful achievement. Thank you. There are so many other RTX games coming your way. Developers all over the world are working hard on RTXing. We're going to have all kinds of amazing games coming your way. Well, I guess your question is this. What are you going to run it on? What are you going to run all these amazing games on? Well, let's show it to you.
Два вентилятора на рельсах. Все-таки GeForce RTX, ну все. Никакого RTX. 28 чипсетов.
Ladies and gentlemen, 10 years in the making, the GeForce RTX 20 series, computer graphics reinvented. Isn't that beautiful? The craftsmanship is unbelievable. The craftsmanship is unbelievable. This is the best design we have ever done. Everything from the voltage, the power regulation, and the thermal management system, it is designed for overclocking. Crazy amounts of overclocking. Not to mention, it is just so quiet. Even when you're maximum overclocked. At maximum overclock, it sounds like 1/5 the audio levels as a 1080 Ti. It is so quiet. The engineering is just absolutely incredible. We're announcing 3 models today. We're announcing 3 models today. The RTX 2070 with 6 gigaраys per second, 5 times that of a Titan X. 5 times that of a Titan XP. 45 trillion RTX ops per second. 45 trillion RTX ops per second. That is several times the performance of a Titan X. 8 gigabyte frame buffer. RTX 2080, 8 gigaраys per second, 60 trillion RTX ops, about 6 times the performance of a Titan X for ray tracing, 8 gigabytes, and then the RTX 2080 Ti, 10 gigarays. I love gigarays. 10 gigarays. Shoot as many rays as you like. Go crazy, just shoot rays. 78 trillion RTX ops, 11 gigabyte frame buffer. Starting at $499. Starting at $499. Pre-orders today. On shelf everywhere, September 20th. And here is your Nvidia RTX family. The Nvidia RTX family. The Nvidia RTX family. The Nvidia RTX family. Ladies and gentlemen, soon I'm going to see the Nvidia RTX family. The Nvidia RTX family. Quadro 8000. Quadro RTX 8000. 2 GPUs connected by NVLink, turning it into one large virtual GPUs. 96 gigabyte frame buffer, 166 trillion RTX operations. 166. That is basically 16 Titan X's in one PC. $20,000. $20,000. Now just imagine, that is twice the ray tracing performance of a $68,000 DGX station. Twice the performance of a $68,000 supercomputer. Then you have the GeForce RTX family. The 2080 Ti from $999. The 2080 from $699, and the 2070 from $499, and the 2070 is higher performance than the $1,200 Titan XP. look at it this way. I want you to look at it this way. Look at this. This is what they look like. The biggest generational leap in the history of computer graphics. Our beloved Pascal, the best GPU the world had ever seen, next to the Turing family. It is a shocking contrast. 10 years in the making. So, ladies and gentlemen, the RTX family. So proud of it. Well, that's our show. The GeForce RTX, the first to implement the Nvidia RTX platform, reinventing computer graphics using this hybrid rendering mode of rasterization and ray tracing, compute using CUDA, and artificial intelligence. Artificial intelligence that was trained using supercomputers. And all of those neurons and all of those weights from all of that experience then sits inside your PC, and it generates images that no possible software written by humans could do. And it generates beautiful images. The Turing, the largest generational leap in the history of our company. The most important new GPU we've created in 10 years since CUDA. 78 tera RTX ops. 78 trillion ops. Basically, changing things so dramatically, we have to change the way that we talk about performance. Because in the future, you're going to ray trace parts of the image, you're going to rasterize parts of the image, you're going to use post-processing on some of the image, and you're going to use artificial intelligence to generate all kinds of pixels that are impossible to generate otherwise. And the GeForce 20, the GeForce RTX 20 series, starting at $499, available everywhere on September 20th. What do you guys think? Okay, I have one more surprise for you. The guys did something. Well, everything is real time. It's physically based. All the materials are modeled properly. Reflections just work. Inner reflections just work. The lighting just works. Ambient occlusion just works. Area lights just works. Have I told you that before? Lighting, reflections, shadows, it just works. Everything could be dynamic, no cooking necessary, no art necessary. Just turn on the lights. Enormous amount of computer graphics capability then kicks in and draws the rest of it. Everything you see here is all completely in real time. Ladies and gentlemen, have a great Gamescom. It's been a pleasure being with you. This is a historic moment. Computer graphics has been reinvented. Thank you very much.
and